know about the problem of polymerizing amino acid residues?
What did you say?
Look, you know what a long-chain molecule is.
Oh, what?
Do you know what a molecule is?
No. Something like an atom.
That's it. Atoms stuck together. In this case, like a long chain. Now, cotton and silk and every natural fibers is made up of these chains. And recently, we've learned to make artificial fibers with even longer chains, such as rayon and nylon. You've heard of nylon. Well, I think I've succeeded in the copolymerization of amino acid residues and carbohydrate molecules, both containing ionic groups. It's really perfectly simple. I believe I've got the right catalyst to promote interaction between the reactive groups at the end of the peptide.
It's not just mad scientists and Ealing communists who are interested in polymers and copolymerization. Polymers play a major role in our modern industrial society. Well, I'm sure you can recognize a polymer when you see it in terms of a plastic bucket or washing up bowl. But what are these polymers on the molecular level? Well, as the man said, they're long chains. And just like this chain, the polymer is made up of links of monomer units that are covalently bonded together, one after the other. Now, the important thing about these chains is that they're very long, on average being, say, 5,000 monomer units long, like this chain here. Many natural materials are polymeric in nature, such as protein, RNA, DNA, and polysaccharides. But it's the synthetic polymers that we're interested in, such as the polypropylene used to make this chain. So the question arises, how do we make these polymers? Here's one of our monomers, and here's another. Now, the first thing you need to make a polymer chain is a lot of links, that is monomers. And the second thing you need is an initiator, and that's me. The polymer chain is made in exactly the same way as the polypropylene chain was made. That is by forging on links, that's monomers, one at a time. The action repeating itself time after time. There's another way of making a polymer chain, and as before, we start with lots of monomers. But this time, growth occurs in steps, and we don't need the initiator.
You've seen what a polymer is, and two ways in which such long chains can be built up. And I hope that you notice the difference between the two methods of construction. In the first, called chain growth, the chain structure was clear from the outset. Growth only occurred from the reactive end. Only the person on the end of the chain could extend its length by joining with someone else who then became reactive. Step growth was much more anarchic. The monomers didn't have to wait around till they met a reactive end. Anyone could join with anyone else. So there was a difference in the chemical construction of the two polymer chains. And this leads us to a second important point. In chain growth, the monomer was either uncombined, part of a growing chain, or else part of a dead chain. That's a chain that's complete. In step growth, the monomers began to link from the outset, and so the solution contained growing chains of various lengths, trimers and tetramers, which then go on to react to give the larger molecules the higher oligomers. Now, the first of these reactions, chain growth, can be realized chemically by one of three different reactions: anionic, cationic, or radical polymerization. We're going to look in more detail at radical polymerization because it's the easiest. Now, in radical polymerization, chain growth occurs by three steps. The process begins with initiation, the formation of the reactive site, which is passed down the chain as it grows. This growth step is called propagation. And finally, there's termination, where the chain is prevented from growing any further. A clear example of this is the polymerization of ethene to give polyethene, polythene. The radical initiator is benzoyl peroxide. The action of heat or light cleaves the oxygen-oxygen bond to form two benzoyl oxy radicals. These are unstable and lose carbon dioxide. The resulting phenyl radicals initiate chain growth. Ethene monomers can then add on. One of the electrons from the double bond goes to form the bond to the attacking radical. The other electron forms a new radical. And so the process is repeated time after time. Chain growth stops when two radical ends react together, forming a stable polymer. You've seen an example of step growth polymerization in an earlier television program. Step growth usually goes by very simple chemical reactions, such as the formation of amide bonds. And the polymerization which we hope will be familiar to you is just one way of synthesizing nylon 6,6. Hexane dioyl dichloride reacts with hexane 1,6-diamine by attack of the nitrogen lone pairs on the carbon atom. Proton transfer gives a tetrahedral intermediate. HCl is then eliminated to form the amide linkage. As all monomers have a reactive site at each end, a long polymer chain quickly builds up, step by step. Different products require polymers with different properties. Often, several need to be combined in the same object. This needs to be tough and durable, flexible enough not to break, rigid enough not to distort. It needs to keep its shape precisely if the quality of sound reproduction is not to decrease. And it mustn't be too sensitive to temperature, otherwise it will warp. But so far, we've only been concerned with the properties related to the end use of the product. Now, PVC is the major constituent of gramophone records, and as such meets these demands very well. But often, these conflict with the needs for its manufacture. The microgrooves of modern LPs requires that the material from which the gramophone record is molded should faithfully follow the tiny modulations of the master recording. PVC does not have excellent flow properties. The solution to this is to mix the PVC monomer with a small amount, say 15% of ethinyl ethanoate. This improves the flow properties of PVC without detriment to its other good properties. But it's not just a question of physically mixing the two polymers, although this is done in certain circumstances. A much more stable and radical alteration of the properties is achieved by a chemical combination, copolymerization. But I should stress that copolymerization is just one solution to the problem, but it's a chemically intriguing one. Let me show you how the properties of a copolymer can be radically different to the properties of a homopolymer made from the same monomers. The two monomers we've chosen are phenylethene, that's styrene made from phenylethane, and butadiene. Both are products of the petrochemical industry split off from crude oil at plants like the one at Grangemouth. Now, styrene is a liquid and butadiene is a gas at room temperature, but on polymerization, their properties change drastically. The homopolymer of styrene, polystyrene, is probably more familiar to you in its low-density form, used for ceiling tiles or packing material. This is high-density polystyrene. It's tough and hard, brittle and inextensible. This is polybutadiene. It's a rather soft, gummy material. It has to be handled between these two cellophane wrappers because it's rather sticky. Clearly, these two polymers have very different properties. So what happens if we physically mix the two together? Say, mix powdered polystyrene in a polybutadiene matrix. Well, we get this material. It's soft and gritty, without the extensibility of polybutadiene and the strength of polystyrene. Clearly, that's not a useful exercise. So much for physical mixing. What about chemical combination? Well, there are a number of ways in which a population of two different monomers can be combined to give a copolymer. Here's one. This time, there are two sorts of monomer. The youngsters in red shirts are one sort, say styrene, and those in the white shirts are another, say butadiene. The rule here is the monomer at the end of the chain can join with any other monomer, be it styrene or butadiene. The chain is randomly arranged. Here's a sample of such a copolymer made from styrene and butadiene. It's called SBR, for styrene butadiene random copolymer. It's probably more familiar to you as synthetic rubber. The primary raw materials for SBR synthetic rubber, phenylethane and butadiene, are piped to the plant from a marine terminal nearby. Phenylethane is itself a feedstock from which the styrene monomer will be synthesized in this plant. The product is purified by distillation in fractionating columns. Butadiene is kept on site in pressurized tanks. The styrene is also stored here. Styrene and butadiene are not the only raw materials. It takes many more secondary ingredients to feed the SBR process. Agents to initiate polymerization, to control chain length, prevent oxidation, and to terminate the reaction when it's gone far enough. The whole reaction takes place in an emulsion, a soapy solution containing this natural organic material, rosin. Sulfuric acid will be used to precipitate the rubber from the emulsion. The quantities are large. This is a bulk industry. A plant like this produces 400 tons of rubber every day, and it works round the clock to do it. This pump marks the beginning of the reaction area. The chemical ingredients have already been made up and reached the area at the correct concentrations, temperatures and pressures. The manufacturing process is continuous, and the pump is a metering device, controlling very accurately the rates of flow of the components into the reactor line. It is vital that ingredients reach the reactors in the correct proportions. On leaving the pump, they are cooled. The chemical reaction they're about to undergo is exothermic. In the reactors, the mixture is constantly stirred and cooled. These vessels are the reactor line. The mixture flows through them slowly. It takes about 10 hours. This process is a free radical polymerization. The radical end reacts randomly with styrene or with butadiene. This one's styrene. Butadiene can add on in two ways. Addition can be in the 1,2 mode, alternatively it can be 1,4. The product is a random copolymer consisting of 30% styrene and 70% butadiene. 2/3 of the butadiene in the completed molecule will be in the 1,2 configuration and the remainder in 1,4. The isomers are scattered randomly throughout the long molecular chain. At the end of the reactor line is a set of much smaller displacement columns. They represent the fine-tuning of the process. The reaction can be stopped in any one of these columns when the desired chain length has been reached. In a continuous process like this, regular sampling is important. This is the first time at which the actual product sees the light of day. This is our copolymer. It's still in fine droplets mixed with the soap solution. In this state, it's known as a latex and is very similar to the natural product. Most of the latex passes on for coagulation. Mixing the latex with acid and brine precipitates the rubber in solid form, the crumb. It only remains to wash the crumb from the acid and to dry and bale it. This machine wrings the water out of the crumb, squeezing it under high pressure. By the time the crumb has gently jogged up the spiral elevator, it will be dry enough to be weighed and baled. Oil has been added to this crumb to improve the mechanical properties of the rubber for the end user. It takes 36 kilograms of rubber to make each bale. More than 60% of the output of this plant will eventually form parts of car tyres. But it's not yet ready to hit the road. Why not? Well, the answer has to do with vulcanization, sometimes known as curing. Now, Vulcan was the Roman god of fire, and vulcanization involves two attributes of volcanoes, heat and sulfur. Now, here's our sample of SBR before vulcanization. It's soft and weak. And before vulcanization, we can regard the molecular structure as being like a long folded chain. It's a tangled mass and has no resistance to deformation. Sulfur is added to the SBR and the mixture is heated up. The sulfur molecules make rigid bonds between sections of the long SBR molecules, giving them a rigid structure. What happens now if a force is applied and then removed? The molecules now resist deformation. They are elastic. The material returns to its original conformation. Here's a sample of vulcanized SBR. It's much stronger and more elastic than the raw sample we saw earlier. And it's vulcanized SBR that does meet the road. Of course, it's mixed with other ingredients, carbon black to give it strength, antioxidant, filler, plasticizer, 101 different substances added at the blending stage of manufacture. But vulcanized SBR has one drawback, and that's its permanence. After vulcanization, the material can't be remolded, so it can't be recycled. So wouldn't it be useful if there was a way of arranging the two monomers so that the cross-linking was an inherent property of the polymer? And wouldn't it be even more useful if it could be recycled? Well, there is another way of arranging two different monomers. This time, there's a block of red monomers, followed by a block of white monomers, and another of red. It could be the other way round. configuration is known as a block copolymer, and the properties of our styrene, butadiene, styrene, SBS block copolymer are very similar to those of vulcanized SBR. But unfortunately, we can't use it for car tyres for reasons which we'll see later. But first, let's look at the chemistry behind SBS. A copolymer can also be built up by a chain growth mechanism. First, styrene monomers add on one at a time. Then butadiene monomers. Finally, styrene monomers again. That's one way of producing SBS, but there is a second route. Styrene and butadiene can be polymerized to form a diblock copolymer. This reacts with phosgene, a coupling agent, to give an acid chloride. But this acid chloride can react again with another diblock. The product is our SBS block copolymer. Dichlorodimethylsilane is an alternative coupling agent. The silicon behaves just like a carbon atom and undergoes an SN2 reaction. As you saw, the chemical route by which a copolymer is synthesized has implications on the way in which the monomers are arranged in the polymer chain, and this in turn must affect the physical properties of the polymer. Here's our sample of SBS. It's much stronger and more elastic than the uncured sample of SBR, which is made from exactly the same monomers. In the SBS, the styrene ends of the molecule coagulate together. We say they crystallize together, locking the chains together. This acts in exactly the same way as the sulfur crosslinks did, and stops the chains slipping over each other when the material is stretched. Unfortunately, at high temperature, the domain structure breaks down. The styrene domains melt and no longer hold the chains together. On cooling, the polymer takes up a new shape. Clearly, this isn't useful for car tyres, but it does find itself in contact with the road in another form. SBS is ideally suited for the footwear industry. Its durability is good, it can be injection molded. It's tough, light and flexible, and its low temperature properties are ideal. Of course, it's not used in the raw state. It's mixed with antioxidant, extender oil, filler, and even other polymers, before being molded to something like this. At present, only 10% of shoe soles are made from SBS, but it's a growth area. There are many copolymers, and even more applications for them. And, like all plastics, we wonder what on earth we did without them.
Blooming.